Okay, so we're on to the final one then. Step support assignment number 25. And despite the fact that this is integration, I actually really enjoyed this one. This was a nice question. So we're going to start by showing this thing at the top here by doing this substitution. So let's do it. Theta is a quarter pi minus phi. So there it is. D theta then is minus 1, or d theta by d phi is minus 1. That differentiates to minus 1, obviously. So then times by d phi, and you get d theta is minus 1 d phi. So I'm ready to substitute that d theta in with this. I'm also obviously ready to substitute this theta in with that, but there's a third thing I need to change, which is when it's a definite integral, you need to change the limits. So let's change the limits. When theta is a quarter pi, theta is this, so a quarter pi is equal to this, and we get phi is 0. And when theta is equal to 0, we get 0 is equal to this, which means phi is equal to pi over 4, or 1 quarter pi, which is interesting because it means these limits actually change over. When theta is this, phi is 0. When theta is that, phi is that. So yeah, they actually change over. And of course, now I replace the theta with this, and I also replace the d theta with minus 1 d phi. Now this minus 1 can obviously come to the front, and that's helpful because I have a rule for integration, which is the integral of f of x from a to b is the same as the negative integral from f of x from b to a. So I can swap these two over and get rid of that negative sign, just like so, which is great. Now, I don't really like this compound, so what I'm going to do is I'm going to get rid of it. Now, if you're doing step and further maths, you just need to have stuff like this in your head walking into your exam room. So, okay, in this case, I've got a is a quarter pi, and b is minus phi. So put those all in the right places. And now two things here. Firstly, tan over quarter pi is 1. If you're still more comfortable working in degrees, pi is 180 degrees, so quarter that is 45. So you get tan of 45, and maybe you know that's 1. Now, the other thing we need to know is that tan, just like sine, is an odd function. Tan of minus x is equal to negative tan x. Cos is the even one. That doesn't make a difference when you put a negative in, but tan changes like sine does. So here, to make that a phi, I need to put this negative out to the front to change that to a negative, and here to make it, I need to put that negative out to the front, which of course makes that positive. And remember, this was 1, so it's 1 plus tan phi, and this was 1, so it just goes away because you're multiplying. So it's 1 plus, sorry, it's 1 minus because this changed that to a minus, over 1 plus because that changed to a plus. And we end up with that thing in there. Now, this doesn't seem better than this, but it's what they asked us to do, so let's continue. I can put these fractions together by making the 1 a 1 plus tan phi over 1 plus tan phi. And now we have a glimmer of hope because when we add those numerators, we see that those two tans cancel, and we end up with 2 over this. Now, looking at what we start with and looking at what we have now, this looks worse. It looks like we've made the problem worse. Because instead of having a 1 plus tan theta, a log of 1 plus tan theta, we've got a log of 2 over 1 plus tan theta. So, but I mean, they told us to do this substitution, so it must work, right? So how do we get this to work? We haven't made a mistake. So how do we get this to work? Well, we remember we've done a lot of trig so far using these tans, but there's another type of function in this integral, which is the log function. So what log function rule can I use here that will be helpful? Well, I know log of a over b is log of a minus log of b, right? So here, this is log 2 minus log of 1 plus tan theta. And this is good because I know how to do this bit. When I split this up into two integrals, I know how to do this integral here. Like, this is nice and easy. Now, this isn't easy, but look at it again for a second. Is that not, if I just put this down next to what I started with, I know how to do this integral. Is this not the integral that I started with? I think it is, right? Now, it almost is, except for the variable is phi instead of theta. And we have to ask ourselves, does that actually make a difference? And I mean, the answer is no, right? Phi is just a dummy variable. You can replace it with anything you want because this is a definite integral. And let me show you why. If I'm integrating x dx between 1 and 2, x obviously integrates to x squared over 2. And then the fact that you put these limits in here, you replace the x with a 2 to make 2 squared, which is 4 over 2. You replace the x with a 1 to make 1 over 2. Means that you just end up with numbers at the end, right? This variable just went away. You used it to do the integrating bit, but then it just goes away when you put the limits in to just end up with a number. And so when you do the integral of y dy between 1 and 2, the same thing is going to happen, right? You end up with this function, which looks different to this, but then you put the numbers in and it just means it becomes the same, right? So if we're going to integrate Taylor, d-Taylor, between 1 and 2, Taylor integrates Taylor squared over 2, and then you put your limits in to get 2 squared over 2 minus 1 squared over 2, which is the same number. So it really doesn't matter what you put in here if you're doing a definite integral. You're just going to get the same answer because the integral is just there for show, right? It's just there to show you where to put the numbers at the end. So I can replace this with a 1 plus tan theta d theta. Not going to make a difference. But now, of course, I'm more comfortable about the idea, well, this is definitely the same as this, which means I can just add this to both sides to get 2 lots of this on this side equals the integral that, remember, I know how to do. Which means, of course, I can just divide both sides by 2 now to get half of the integral that I know how to do, which is great because now I'm there, right? Just integrate this. This integrates to phi log 2 between these two things. Put a quarter pi in there. When you put 0 in there, of course, you get nothing, so that doesn't matter. But put a quarter pi in there, times by a half to get pi log 2 over 8, which is what they were asking me to do. Okay, part 2 then. Now, this looks like a really complicated integral. However, if you've been shown this, and even better, if you have definitely the right answer to it, they're expecting you to use this somehow. Like, that's what they want you to do. So how are we going to do it? Well, notice here, this is log 1 plus x. Here, the thing that I know how to do is log 1 plus tan theta. So what happens if I just replace the x with a tan theta? That at least makes the numerator the same structure as the thing that I know how to do and know the answer to. So let's replace the x with a tan theta. Let's make this my substitution. Now, of course, this means dx by d theta is sec squared. That's the result you just need to know. And of course, sec squared is 1 over cos, which means dx is sec squared theta d theta. So I'm ready to replace that with this thing here. Of course, I'm ready to replace the x's with tan thetas, but the last thing I need to change about this is the limits, of course, just like last time. So when x is 1, what's tan theta? When x is 1, what's tan theta? Well, we've seen this before. We did it the other way around. Theta is pi over 4. And when x is 0, 0 is tan theta, which means theta is 0. And so my new limits become pi over 4 and 0, which is amazing because that also lines up with the limits of the integration that I know how to do, which means this is probably on the right track. Okay, so I've replaced the dx with a sec squared d theta, and I've replaced the x's with tan thetas and tan squared thetas, which is good. Now we need to know another result off the top of our heads, which is 1 plus tan squared is sec squared. And this means I can just replace that with that and cancel it, and I end up with this integral, which is amazing because that is the exact integral in every way that I know how to do, and I get my answer. I think I have a video on this in case you're interested. I think I have a video on this as well, which you can find if you want to. Okay, third integral then. So this integral, the one we just did, by the way, that really wasn't that tough, as long as you spot this substitution, as long as you spot how to make the one that you know how to do into this one. And that's kind of what STEP tests. So really not that tough as long as you spot that substitution. What about this one now? So this is, again, it's about spotting the right substitution. Now, it's not obvious to me how to make this fraction into a 1 plus tan theta. That's not obvious to me at all. I mean, you've got lots of time and steps, so you can try some stuff, but I can't really work out what I'm supposed to do with that. However, even if I could, it's all irrelevant unless these limits match up, right? Because when you know an integral, when you know the value of integral, it's not just the function inside the integral that's important. The limits are just as important. If the limits were out, this number would be different. So I need to make these limits. Otherwise, my substitution would be worthless anyway. So, well, how do I get from here to here or from here to here? Well, I double it, right, to get from there to there. And I guess I double that to get from there to there. So why don't I just try a basic substitution first of x is 2y, just so that I can maybe try and match these limits. Now, of course, this means dx is 2 dy. And changing the limits, if x is pi over 2 or a half pi, pi over 2 is 2y, I'm saying, which means y is pi over 4, which is excellent. That means my new top limit is this. And now, of course, when x is 0, 0 is 2y, which means y is 0, which means my bottom limit matches as well. So that's perfect. Now, what sacrifice have I made there? Well, x gets replaced with 2y both times. And of course, this dx gets replaced with a 2 dy, which doesn't matter because that 2 just moves over to the front and it's fine. Now, what about these 2y's in here? Now, this function here that I know how to integrate definitely doesn't have any 2's in here. So I feel like I need to get rid of these. I need to go back to my basic sine, cos, tan functions if I'm going to have any chance of getting to here. Now, dealing with sine 2y is easy because that only has one expression for itself, really, that you want to be using, which is 2 sine y cos y. So I can replace that in there easily, and I can also move this 2 out to the front, like I said. Now, cos 2y is always harder to deal with because there are 3 equations or identities for cos 2y, and they're all quite useful lots of the time. So I need to think, well, which one feels to me or looks to me like the most useful right now? And this one is calling out to me because it has a -1 in it, which means if I put it into here, it's going to cancel with that +1, right? 1 minus 1, and I end up with a single term on the denominator, right? And even if I just try one of these things and it doesn't end up working out, again, like I said, you've got lots of time in step, just try one of the other things. Don't get a ton, just try something else. But this one called out to me because of the -1. Now, what can I do here? Well, I have this number plus this number over a single denominator, which means I can split that fraction into these two fractions, right? Because same denominator here means I just add the numerators and I end up with this. Now, why have I done that? Well, looking at this thing here, that 2 cancels with that 2, and that cos y cancels with one of the coses from down here. So this will end up being sine y over cos y, the one cos that's left over. Now this, we've already seen, 1 over cos squared can be written as sec squared. That's just the identity for that. And now another trig rule that we need to use that we haven't in this video yet is that tan is sine over cos, which means this thing here is tan, which is great because now I have at least the makings of this here, right? I've got something plus tan in the log. Like I haven't got the 1, but I've got the tan now, which is great. So this, it feels to me, I've got the limits in the right place. It feels to me like I'm onto a winner here. I'm gradually getting this to become this, I think. Like I've made a lot of progress from here for sure. Now, what do I do here? Well, I remember a rule I've already used today, which is sec squared is 1 plus tan squared. So I can replace this here with a 1 plus tan squared. And now I can also write tan y as 2 over 2, 2 tan y over 2, because now I've got a common denominator and I can add these numerators together. And now I highly suggest that you pause the video here and really try this to finish this off on your own, because I think you can do it. Nothing I'm going to use in the rest of this video I haven't used in the last 10 minutes. So if you're stuck, just go back through the video and try and find the thing that's going to be helpful. But I really think you can all finish this off from here. The first thing I want to do is notice this is a log of something over something. And I've used that rule before. Log of something over something is log of the top minus log of the bottom. So this is log of this thing minus log of 2. Next thing I'm going to do is, well, this is just taking away a thing. So I can split the integral across those two things. So it's 2 integral of this minus 2 integral of that. And now make a mental note, we can all do this. In fact, we've already done this exact integral in this video. So we can all do this. Now, what about this over here? And if you spotted this, really well done. This thing inside of this, that factorizes beautifully. It factorizes, and you've got the hint because it's about an inch up the page there. It factorizes into 1 plus tan y all squared. Because of course, if I expanded that out, it would be 1 times 1 is 1. Tan y times 1 plus another tan y plus 1 from the other two makes 2 tan y. And then tan y times tan y is tan squared y. Right? And now I've already started doing this integral. You just say it's y log 2 and then ready to put the limits in. But this is the important bit here. And now how do I finish this? Well, we have another log rule, which is log of something squared, or to any power. You move the power down, bounce the power down to here. Which means this is 2 log of this thing. And again, I've just put the pi over 4 into here and the 0 into here, pretty self-explanatory. But now focusing on this still, this 2 can just move out to become 4 lots of, and I've put this in red because I'm so happy with it. That is exactly what I know the answer to. I've done this a couple of times now. I know the answer is this. Of course, this goes away, times that by 2, you get pi over 2 log 2. But this, I know the answer to is that, so I'm going to put that in. 4 times pi over 8 is pi over 2, and I end up with a beautiful answer of 0. Really well done if you managed to finish that off. Really well done if you just did it entirely without my help. But yeah, I thought it was a really lovely question to finish the STEP support program on. So yeah, that's the end of the support program. Really well done if you watched all the videos and finished it. I mean, this isn't really the end, which I'm sure you're incredibly pleased to know. On both this channel and Mr. Winfield's channel, there are tons of step 2, step 3, and more step 1 questions as well. So please get your teeth into those, have a good practice of them, and you'll be all set for your future step papers. But yeah, really well done for watching this entire series.